why we explore Mars, the mysteries of the red planet, the history of water, the possibilities of life.
You learn something and then you design the next mission based on what you learn.
Has allowed us to literally go back in time on Mars.
The first picture will cover an area of 176 miles.
Mariner 4 began transmitting back images.
The first photograph that a human being has ever seen from the surface of another planet.
On August 20th, 1975, the first Viking spaceship was launched.
You are seeing something that no other human has ever seen before.
Former seas and mountains.
Huge canyons.
That sense of wonderment and achievement and always working towards your goal.
We can do, and we will do.
And liftoff.
Touchdown confirmed.
Mars is unavoidably special.
We've landed and we've scooped.
We've roved, we've orbited.
Together, we did it. But the attitude was together we can do it.
The future is what you make out of it. You can make it real.
And here we are with Mars Perseverance, 51 years later, getting ready to do the first ever Mars return mission.
Eventually, we can bring those samples back to Earth and determine for the very first time, did life exist on Mars?
Hello, and welcome to NASA's Kennedy Space Center in Florida, where we are just days away from launching NASA's next Mars rover, Perseverance. Now, Perseverance is just one part of a larger strategy to understand the red planet. Scientists have been waiting for generations to bring back samples from the surface of Mars. So we're here today to talk about why scientists want to bring those samples back to Earth and how we're going to do it, starting with the Perseverance rover. I'm Jari Cook from NASA's Jet Propulsion Laboratory in Southern California, and I'm here today with a panel of experts who can talk about our plans for Mars sample return with our key international partner, the European Space Agency. So I'm going to introduce our panelists today, starting with Thomas Zurbuchen. He is the Associate Administrator for NASA's Science Mission Directorate. He's going to talk about the overall strategy for Mars sample return. Next, we have from the UK, David Parker. He is the Director of Human and Robotic Exploration from the European Space Agency. Dave is going to talk about why ESA is partnering with NASA and also what their role is. Next, we have at NASA headquarters, Jeff Gramling. He is the Mars Sample Return Program Director, and he's going to talk about the NASA components to this campaign. Next, we have Julie Townsend at the Jet Propulsion Laboratory. She is the Sampling and Caching Operations Lead for the Mars 2020 Perseverance rover, and she's going to talk about what the rover is going to do on the surface of Mars. Next, we have Chris Hurd. He is a return sample scientist, and he comes to us from the University of Alberta in Canada, and he's going to talk about what kinds of samples we want to collect from the surface of Mars. And then we have Lisa Pratt. So she has probably one of the coolest titles at NASA. She is the Planetary Protection Officer at NASA headquarters, and she's going to talk about how we're going to do this all safely. So we're going to get started by first talking to Thomas, who recently was just back from the launch pad.
It's very cool. You know, I was just standing out there in the sun. It's pretty warm, and I saw the launch vehicle go from its vertical integration facility about 1,000 yards over to the place from where it's going to go in less than 48 hours into space. And I was there with some of our leaders from JPL, some of our leaders from NASA headquarters, but especially the leaders from ULA. And I just couldn't tell you how proud we are to get to this important moment. Of course, the most important thing is yet ahead, which is to take off this planet and go to its destination, the red planet, our neighborhood planet Mars. And just before I talk about Mars sample return, I just want to tell you how excited I am to have Dave Parker on the phone. Really our friend, personal friend of mine, and international collaborator, and a really critical part of the Mars sample return campaign that we're going to talk about today. Dave and I are talking on a regular basis because so often our relationship really is one of the many ingredients that built a team that also there will be successful with Mars sample return. Jeff Gramling is on the phone as well. He just introduced him. And I just want to just say how happy I am that he joined as the first director of the newly created Mars sample return program at headquarters. The way we're organizing that includes all the lessons learned from complex programs that we've had, whether it's Mars 2020, the James Webb Space Telescope, or other programs. And he's going to have a really critical role in this. And I just couldn't be more happy to have him on board. What we want to talk about today, though, is shown here in the first image, is the samples. We talk a lot about Mars 2020 and instruments and so forth, but it's all about these samples. You see these sample tubes that are right there on the ground on this Martian soil in this artist's depiction that we're going to talk about. And of course, the goal is to not keep them there on the surface, but to get them back into the best laboratories that we have, that humanity has, which are, of course, all the labs here on Earth. And the next video provided by ESA is telling us how we're doing that. Of course, the first element is to go with Mars 2020 to the surface of Mars and create those, get those samples. There's another spacecraft that is landing, and it's launching from the United States, and it's landing a launch vehicle and a fetch rover that's collecting those samples and bringing it back to that Mars ascent vehicle, a MAV as we call it, and that takes off in this kind of game-like simulation and drops off this orbiting red container that is orbiting Mars. And you see immediately a European-built spacecraft that had taken off from Europe is catching it and is bringing it back to Earth in a long orbit, much longer than can be depicted here, back to Earth into the range in Utah and then into the labs, from receiving facility into labs. And so these pieces, 4 launches, multiple spacecraft, together make the Mars sample return campaign, which frankly is the manifestation of a lot of dreams and aspirations of the science community. In fact, the highest priority of the National Academy's decadal that we're working under, and we're so excited to make progress on it now. The samples from Mars have potential of profound change of our understanding in the origin, evolution, and distribution of life on Earth and elsewhere in the solar system. And even now, NASA continues to study moon samples that were brought back from the Apollo program with new questions and more profound insights that still fill journals today. And we just can learn from that how important these samples are going to be, not just for the questions that we're currently imagining, which are profound by themselves, but also for questions that frankly are going to come up because we look at these samples and because we make progress of Martian science elsewhere. And so the implications of what we know about Mars and the search of life are enormous. And even after Perseverance accomplishes all the things on its science list, it only sets it up for this important part of this return of these samples to Earth, which is really the subject of this meeting here. And what I'm going to do now, Dave Parker, is kick it over to you and just have you talk about your excitement and the role that our important partner, the European Space Agency, has in this. Dave, over to you.
Hi there, Thomas. It's great to hear you and see you. I'm really sorry I'm not there with you at the Cape for the launch. Indeed, I'm not even in my office at the European Space Technology Centre. I'm working from home during the current situation. But we're persevering, we're keeping going, and even over here, we're working hard on our Mars program. And I'm really super excited to join you for this press conference. Thank you for the invitation. Being just days away from the launch of Perseverance, any launch to Mars is exciting. But for me, this is excitement times 10 because it is the first part of Mars Sample Return, MSR. And perhaps nearly 20 years of studies and preparation to this moment where we're going to start the real campaign. Now, hopefully you know that ESA is a club of 22 European countries who pool their efforts in exploring and using space for everyday life. And I should add that Canada is an associate member, and you'll see the Canadian flag on some of my graphics. And this is important because Canada is also part of the MSR story via ESA. So within the huge range of different projects that ESA undertakes, from monitoring our changing climate with the Copernicus constellation, providing global navigation with Galileo, and mapping the positions of 1 billion stars in our galaxy with the Gaia mission, MSR is part of the exploration program, for which I'm responsible, and we're able to work day by day with NASA on that program. So if I have the next graphic, please. I would say our space exploration program focuses on destinations where humans will one day live and work. This means low Earth orbit, where we've been living and working on the space station for nearly 20 years now, and the moon, where we are a partner of NASA in the Artemis program, going forward to the moon. And then finally, Mars, the horizon goal for humans, where we already have 2 robotic missions there, circling the planet, understanding this other world. And to emphasize this international cooperation aspect, I point out that today we've announced that 2 of our ESA astronauts will fly on the NASA new commercial crew vehicles to the space station starting next year. And that's in exchange for us providing the power and propulsion for NASA's Orion spaceship to go to the moon. So, as Thomas has said, there's going to be fantastic science out of MSR, but it's also truly an exploration mission in the grand tradition. We have Mars as our horizon goal for humans, but before sending humans, it makes sense to do a round trip with robots, as scouts are precursors. It'll tell us a great deal. You can also almost imagine MSR is kind of a scale model of an eventual human boots on the moon project. Next graphic, please. So explain where we are now at ESA, at European Space Agency, with our Mars program. I said we have 2 orbiters there today. The Little Mars Express has been there since Christmas Day 2003. The Trace Gas Orbiter, which is the biggest beast around the planet today, is doing great science and also relaying data for NASA's Curiosity and InSight missions. And even today, there have been 2 new papers published from the ExoMars Trace Gas Orbiter, intriguing new results about the atmosphere of the red planet, completely unexpected results. And meanwhile, we're working with our Russian partner Roscosmos to prepare the launch in 2022 of the Rosalind Franklin rover, which will search for the evidence of past life using a drill that can get 6 feet below the surface of Mars and therefore below the damage that will be caused to any organic material by radiation, the radiation on Mars. But here, today, we're really here to talk about our contributions to Mars sample return. And it comprises the Earth Return Orbiter, the Sample Fetch Rover, and some important robotics that will transfer those sample containers that Thomas mentioned from one part of the system to the other. It's kind of an interplanetary relay race we're doing. So perhaps I should say more about some of our main elements, the rover and the orbiter. Next slide starts with talking about the rover. So the next slide, please. The Sample Fetch Rover is much smaller than Perseverance or ExoMars or any of the current advanced rovers, because it has the sole task to scurry across the surface of Mars to get those sample tubes and bring them back. And it's a race against time. We only have about 8 months on the surface of Mars to do this, to bring the sample tubes collected by Perseverance back to the Mars Ascent Vehicle and get them off the surface of the planet. And I think you'll see more about these sample tubes later in this press conference. So compared to current rovers, it's got to go a lot faster, about maybe up to 10 times faster. It's got to go autonomously. It's got to navigate its way there and back. And it includes some clever robotics to do the transfer of the sample tubes. Now, we've already placed a pre-development contract with Airbus Defence and Space in the UK to prepare for the Sample Fetch rover, and this builds on their heritage of ExoMars. And this is a message: we're building on the heritage of capability that we already have in this international partnership. So we have to deliver the rover to NASA in 2025 for launch perhaps as early as 2026 on the sample retrieve lander. Our other contribution, shown on the next slide, please, is the Earth Return Orbiter. ERO for short. So this is be launched on a European Ariane 64 rocket from our European Space Centre at Kourou. And it's an amazing beast of a spacecraft, the first interplanetary cargo ship, if you like. And on its cargo deck will be the NASA sample containment system and the Earth entry vehicle that will actually land back on Earth. So the key job of the orbiter, as you've seen from the little cartoon earlier, is to scoop up the sample container that's been thrown overboard by the Mars Ascent vehicle. It's only the size of about a football, a rugby ball if you're British, and then we have to load it into the NASA containment system and fly it home. And also the orbiter does all the telecoms relay and data communications during all the operations on the ground. To give you a sense of scale, this spacecraft has a wingspan of about 120 feet. It weighs 6.5 metric tons at launch. It uses chemical rockets to go into orbit around Mars. The most powerful ion drive electric propulsion system to do the spiraling down to Mars, to spiral back up and come back to Earth. And the news today I can give you, after an intense commercial competition, I can announce that a contract will be placed subject to negotiation with Airbus Defence and Space of France to build ERO. And their team includes Thales Alenia Space of Italy. And together they're kind of the European dream team, because between them these companies have built our Rosetta Comet mission, the Bepi Colombo spacecraft that's on its way to Mercury, and also the ExoMars Trace Gas Orbiter. So coming to my conclusion, really, and I'll hand off to Jeff in a moment, my last slide, I hope I've given you a few hints as to why Perseverance is such an important launch, why Mars Sample Return is going to be a flagship project for the 2020s, and why we at the European Space Agency are humble and proud to have the chance to be a partner of NASA in delivering this extraordinary, mind-bendingly challenging and history-making exploration mission. So thank you, and I'll hand over to Jeff to tell you more from the NASA perspective.
Well, thank you, David. Hi, I'm Jeff Gramling, and I'm really excited to be part of this amazing international team and looking to accomplish one of the most complex things humanity has ever attempted. With the launch of Perseverance this week will be the first step in the mission to bring back the first samples from another planet. Mars Sample Return is a collaboration, as you heard David describe, between ESA and NASA, and we're already working closely with our partners on this historic undertaking. Within NASA, many centers are applying their scientific and engineering expertise to ensure we're successful. As David and Thomas have described, the planned campaign architecture breaks up this round-trip mission into 3 manageable elements that all work together in a synchronized manner. First, the Perseverance rover launching this week will drill and prepare samples and cache them on the surface of Mars. Perseverance will be followed by the launch of the remaining 2 elements as early as 2026. The sample retrieval lander carrying the sample fetch rover will be launched to collect those samples and to bring them to the Mars Ascent vehicle, which will put them into orbit around Mars. This rocket will be the first to launch from the surface of another planet. And we're also working on cool new wheels for the fetch rover. The Earth Return orbiter will rendezvous and capture those samples using a sophisticated capture, containment, and return system, and then bring them safely back to Earth. So now I'd like to show you an animation on how all of these pieces work together to accomplish this feat. So it all begins with Perseverance rover drilling and collecting samples and then caching them on the surface of Mars, with the sample fetch rover collecting them and bringing them back to the Mars Ascent vehicle for launch into orbit around Mars. And then, as you heard David describe, the Earth Return orbiter will capture that sample and bring it back to Earth, putting it into the Earth Return vehicle to bring it back and land on Earth in Utah. All right. The engineering needed to return the samples Perseverance collects is maturing, and it's built upon the past 2 decades of investment in autonomous robots and landing large payloads on Mars. This is why we're confident the time is right for a successful sample return campaign. Just as Perseverance itself is a result of many nations' work, the spirit of Mars exploration and bringing samples of Mars back to our home labs is something we do with the whole world. We look forward to this next step leading to a tremendous leap forward. Thank you. Now I'll toss it over, hand it over to Julie, and she's going to tell you about sampling on Mars.
Collecting samples of Martian rocks and soils and preserving them for return to Earth is one of the most complex things we've tried to do with the Mars rover yet. This is a sample tube. On board the Perseverance rover are over 40 of these, and the objective is to fill each one with a sample of Martian soil or a Martian rock core. I have here an example of a Martian rock, or a rock core, not a Martian rock core, collected in one of our test activities. To me, it reminds me of a piece of classroom chalk, for those of us who are old enough to remember when classrooms had chalkboards. This is a pretty good example of a core. It's largely one piece. It's broken into a couple of large chunks, but it's not pulverized. To achieve this kind of core, we developed a new coring drill for the Perseverance mission, different from the one we sent on the Curiosity mission. Curiosity's objective was to pulverize rocks into a powder so they could be analyzed by the onboard lab equipment. One of the most complex pieces of robotic choreography that we do with the sampling system is what's required to take this sample tube from where it's stored inside the belly of the rover and pass it out to the coring drill on the end of our robotic arm so that a sample can be acquired. This requires the use of robotics inside the rover, outside the rover, and in between. In between, we have the bit carousel. The bit carousel is a dual-purpose mechanism. First, it carries all of Perseverance's assortment of drill bits that can be used for collecting core samples, collecting regolith samples, and abrading rocks. In addition, it provides the mechanism for moving these tubes from the inside of the rover to the outside where it can be accessed by the robotic arm. First, the sample handling assembly, a small robotic manipulator inside the rover, removes this tube from its storage location and inserts it into the lower door of the bit carousel directly into one of our coring or regolith collection bits. The bit carousel then rotates up and presents that bit at the upper door, where it's accessible by our robotic arm and coring drill. The robotic arm and coring drill dock to the bit carousel and extract this bit and go fill it with a sample. Once it's full, we insert it back into the bit carousel, where it's rotated back down to the lower door, and the sample handling assembly takes over again, removing it from the bit carousel and removing it from the bit, and sending it through a series of processing stations inside the rover. The core sample is measured, pictures are taken of it, and then a seal is dispensed into the top of the tube and activated. Once the tube is sealed, it's placed back into storage, where it will ride along with the rover until we reach our caching location, at which point we'll drop it on the ground for the fetch rover to retrieve. So now I'll show you an animation so you can see what our system looks like in action. So here you see the Perseverance rover having just collected a sample from the surface, docking the core with the filled bit to the bit carousel, and the bit carousel rotating the filled bit down to where the sample handling assembly will extract it and move it into a processing station. After it's done this with all of the necessary processing stations, the sealed tube will be placed back into the storage location in the sample tube rack. And it'll stay there for safekeeping until we're ready to drop it off. Now I'm going to hand over to Dr. Chris Hurd, a member of the Perseverance science team, who will tell you more about the types of rocks we hope to fill our sample tubes with.
Thanks, Julie, for that great overview of the really awesome robotic system that we'll use for collecting these samples. Well, I'm personally really excited to be involved in this endeavor. In fact, I've wanted to study rocks from Mars since I was about 13 years old. My role on Perseverance is that of a returned sample scientist. I'm one of 15 such scientists supported by NASA, the European Space Agency, and in my case, the Canadian Space Agency. All of us are experts on teasing out details from rocks in the lab, whether they're meteorites, samples of the moon, or ancient rocks from the Earth that may hold evidence for early life on the Earth. We are trained in the analyses required to answer the fundamental questions about Mars, including whether life ever existed, in our landing site of Jezero Crater, the site of a crater lake and river system some 3.5 billion years ago. So our role on the mission is to help decide exactly where we want to collect samples from within the landing site and to document the context for those samples. We are essentially the documentarians for each and every sample that gets collected. And our goal is to collect at least 20, ideally more like 30 or 35 samples that not only have the potential to show evidence of ancient life, but to reflect a variety of different types of rocks to make a truly compelling suite of samples. Once brought back to Earth, such a suite of samples would keep generations of researchers busy unraveling the secrets of Mars for decades, in the same way that the Apollo samples have done and still do for the Moon. In the meantime, it's interesting that we already have samples of Mars in the form of meteorites, over 140 of them, and I have a graphic that shows one of them. Some of these meteorites have evidence for liquid water having flowed through them at some point in their past, but importantly, the vast majority are igneous rocks, essentially lava flows that were erupted within the last few 100 million years, relatively recently, and much more recently than when the rocks at Jezero Crater formed. The meteorites, don't get me wrong, have provided some fantastic insights into Mars history. However, the Martian Meteorite Delivery Service only delivers certain rocks, because the process involves something impacting Mars and rocks near the point of impact being accelerated fast enough to leave Mars' gravity. And this is a very violent process, and it effectively filters out the weaker rocks that won't make the trip. So we only really get the strong rocks, like the young igneous rocks. The other thing is that we don't know exactly where on Mars these rocks come from. They're from random locations, and so they lack the context. So the great thing about Perseverance is that instead of nature choosing for us, we will get to choose which rocks come back to Earth, along with our careful documentation about where and why they were collected. So I'll turn it over to Lisa now to tell us how we're going to do that safely.
Hey, Chris. Thanks for that cross-border handoff from Canada. I'm Lisa Pratt, NASA's Planetary Protection Officer. The overarching goal of planetary protection is to comply with the Outer Space Treaty and do no harm to a future scientific discovery. Thus, we carefully limit biological contamination of other worlds with terrestrial organisms, and we carefully prevent backward contamination of Earth's environment with potentially harmful extraterrestrial matter during return of samples, either robotically or in the future with astronauts coming back from Mars. For the current Mars sample return, NASA and ESA will implement forward planetary protection based on knowing the microbial bioburden when the spacecraft launches from Earth. In this first photo, you can see the Perseverance rover has been cleaned relentlessly using heat treatment of parts and then wiping the assembled systems and instruments with isopropyl alcohol, as you can see an engineer doing in this photo. By international agreement, we monitor biological contamination of spacecraft by sampling, either wiping or swabbing with a small stick that looks like an oversized Q-tip, and then culturing the hardy spores, which are tiny dormant cells produced by some bacteria. In this second photo, you can see that once a critical part of the spacecraft is heat sterilized, then biobarriers like these shiny wheel covers can be used to maintain the cleanliness of that part during assembly and launch preparation. The tubes for caching samples on Mars are the most stringently cleaned part of the Perseverance rover. You saw Julie holding one of these tubes a few minutes ago. And in this video, you can see the titanium tubes are being examined in an ultra clean room setting prior to heat exposure for many hours at 150 degrees Celsius in order to reach a high level of sterility assurance. So scientists studying the samples back on Earth, like Chris, know that any evidence of life found in the return samples originated from Mars and not as a round trip from Earth. In addition to cleaning treatments on Earth, viable terrestrial organisms that manage to get on the spacecraft despite everything we do will travel through deep space conditions for 7 months on the way to Mars. After landing on Mars, the Martian surface environment will present additional lethality factors for terrestrial organisms, including damaging radiation, aggressive atmospheric oxidation, and bitter cold. For backward planetary protection of Earth's environment, NASA and the European Space Agency will adhere to 3 fundamental rules. Number 1, break the chain of contact with airborne Martian dust. Seals, barriers, microscopic tortuous paths, and scour from solar winds will be used to first limit and then reduce the number of particles on the exterior of the sample return canister. Number 2, robust and redundant containment. In the case of Mars sample return, the strategy is contain, 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 and contain again. There are 3 rugged exterior containers with impact-resistant seals wrapped around the hermetically sealed titanium tubes you can see again in this video. Number 3, inspect and remove the layers of containment one by one inside a specially designed receiving facility where NASA and ESA and the whole world can be assured of the highest levels of biosafety protocols. The decision to land the sample container is no sooner than 2031, and that gives us another decade to continue planning and learning about Mars. At the landing site, we'll be joined by health and environmental agencies to ensure the highest possible level of biological safety during that critical first inspection of the canister, lifting of the canister into a shipping container, and transportation to that very special receiving facility. Scientific experts from many nations will collaborate on initial characterization of the samples while still inside those many layers of containment using various forms of penetrating radiation. Decisions about whether or not there's evidence of a biological threat from Mars samples will again be made in an international collaboration. Let me just close this way. This is the right time for this mission. We've learned enough about Mars from prior missions to design a safe architecture. This is the right mission. 500 grams of Martian material with multiple layers of containment is a very safe strategy. And finally, this is the right team. NASA and ESA are fully committed to safety at each step during landing and transfer to a biologically secured receiving facility. I'll now turn it back over to Jari from JPL.
Thank you, Lisa. All right, so we have some media on the phone, and we're also, just so that everyone knows, we're taking questions on social media with the hashtag Countdown to Mars. So we're going to start with the media first, and we have Paul Brinkman from UPI on the phone lines. Go ahead.
Hello. Yes, thanks for taking my call. I would like to know, obviously, you have a lot of confidence in the technology and the instruments that are going up to identify rock samples. I'd just like to hear a little bit more about what kinds of challenges or difficulties you expect in identifying good places to take a sample.
I think for the difficulties we might face and the challenges we might face for the samples, let's go to Julie at JPL.
Well, there are 2 different kinds of difficulties that we'll encounter. Those are going to be difficulties acquiring the samples, which from an engineering standpoint, which can be range from, whether the rock is accessible, whether it is within the capabilities of our coring drill. But I think that a lot of the difficulties that that were referred to in this question are actually maybe the scientific difficulties of figuring out which rocks are the right rocks to collect. And so I think that maybe we should also toss this over to Chris so that he can give the science perspective on this.
Absolutely, I can speak to that. the team is already right now working with all of the remote observations of Jezero Crater to come up with a sort of a nominal traverse that we're going to take and really pin down those locations that we're really especially interested in. So we'll have a general plan. Of course, we're ready to sort of deviate from that plan if necessary, depending on what exciting discoveries we make. But the idea is to actually have a series of locations that we want to get to and of course potentially sample as well, but explore prior to landing. The actual decision whether to sample is going to be, I think, a fascinating one involving the entire science team, not just the 15 return sample scientists, but the over 300 scientists involved in the mission. It'll be a question of exactly why we want to collect that sample and not another one, and to make sure that we have all that context that I mentioned before.
Great. Okay, we have another media question. Ivan Koron from AFP.
Thank you very much. Do you expect that the science team will maybe be able to say that there was life on Mars based only on the instruments on board, or is it very likely that we will have to wait for the return of the sample? And can you confirm that that should be in 2031?
Take this one.
I'm not sure I 100% understood the question. Do you mind quickly just repeating it to me, Jerry?
Yeah, I'm sorry. Will we have to wait for the return of the samples to be able to say that there was life on Mars, or, does Perseverance have the capacity to
Thank you.
to see it?
So I'm interested in Chris's opinion, but my personal feeling is that even though there will be, in the case that it's really starting to move in that direction, supporting evidence that's coming from remote sensing observations and some of these sophisticated instruments, I do believe that the ultimate proof and the ultimate analyses that are really critical to that question at the level of standard that we need to answer this will come from laboratory analysis on Earth. So I believe this will be a process that will extend over 10 years or so, that where evidence is mounting from remote sensing and in situ measurements up there, but then really culminating in really bringing these samples back and actually, if you want, unwrap the presents once they're really back from a long, long trip. But Chris, anything you want to add to this?
I agree completely, absolutely. I think that as capable as the rover is, that we'll have it really, ideally, if everything goes well, have really intriguing evidence, potentially in the form of organic molecules detected, or even certain structures in the rock that could be indicative that life was there. But to have that definitive proof, we need to bring those samples back and see them in the lab and look at essentially the not only the biosignatures in broad sense, not only the whether there's any fossil bacteria, which is pretty unlikely, but whether there's any sort of chemical signature, organic chemical signature that would truly indicate that life was there.
And that's 2031?
I think Dr. Zabukin can comment on that, but I think the current plans are for the samples to come back no earlier than 2031. Yeah.
Yeah, that's correct.
Thank you.
Yeah.
Okay. Next question is from Marcia Dunn of the AP.
Yes, hi. I just wanted to review the timeline for the sample returns. It's not clear to me whether the Mars Ascent vehicle launches with the Fetch rover, or does it launch separately, and if so, when? And what is the prospective launch date for the return orbiter?
Dave, did you want to take this and just talk about the details on timing? I could do it too, but go ahead.
Yeah, sure. Thank you. So the intention is, well, the first thing to say is going to Mars is challenging, and particularly doing this mission is challenging. You only launch every 26 months. And one of the things you want to avoid doing is arriving at Mars in the middle of winter, because in the middle of winter you can have huge quantities of dust thrown up into the atmosphere, which can really disrupt operations and making a safe landing. So the trick is we want to arrive with the sample retrieve lander carrying the Fetch rover at the beginning of spring and have all of spring and summer on Mars to do our work, and then get back off before the next winter season arrives. So the way it works out is that if we launch in latter part of 2026 with both of the NASA mission and the ESA spacecraft, we end up doing most of the on-surface operations during the latter half of 2028 and the beginning of 2029. Now, that may sound like a big gap. It's because we will take a route to Mars for both of the launches that is not the usual short traverse, but is actually a bit longer than normal. That's both to make it very efficient, but also to ensure that we arrive at the right time. In fact, our orbiter, the Earth Return Orbiter, takes about a year to get into initial Mars orbit, and then we'll use that electric propulsion system I mentioned to spiral its way down to a relatively low Mars orbit, where it can oversee operations and be ready then to rendezvous with the Mars Ascent Vehicle towards the end of the autumn, which in our years is early 2029. And then, again, it takes about 2 years to get home again because we have to spiral out of Mars orbit and then make the return trip. Long answer, but I hope that gives you what you want.
Okay, Jeff, did you have anything else to add on the timing?
Just to follow on what David said, yes, if we launch if we launch as early as 2026, then for the reasons to avoid the dust storms during winter, to gain the efficiencies in both getting there and returning, the earliest return would be in 2031.
We're going to go to social media now. So since we started talking about dust storms, I'm going to hit that question. Singh on Twitter asks, Perseverance will leave samples in test tubes. Will they not be lost in the storms of Mars? So I'm going to ask Julie, how do you guys keep track of these sample tubes?
Well, over our experience on the surface of Mars the past many years that we've been traveling there with our rovers, we've developed good mapping capabilities. And so we will be localizing the location of each of the samples that we drop to within a couple dozen centimeters relative to the orbital map. And so we will know exactly where these things are. They'll be mapped relative to local features that are big enough not to be buried in a dust storm, and they'll be mapped relative to the orbital features that we can see in our orbital mapping.
Okay, thank you, Julie. Okay, so then we have another question from Ziyuan Zhu on Facebook. He asks, how does the mission team decide and prioritize which sample to collect? So, Chris, you were talking about how this is going to be a difficult process, but do you guys have any initial thoughts as to which samples you're most excited about or what kinds of rocks you think you might get at Jezero?
Oh, absolutely. I think the key question here is what we can do with the rover to identify those environments or the rocks that record the ancient environment that was potentially habitable by life. So those will be prioritized, absolutely. That involves exploring, these previously identified sort of regions of interest or locations that we want to focus our attention on. And then with that, we are already establishing a whole series of scientific questions that can be answered by the samples and the investigations that we do. So if we come across a particular sample type, we know we want a particular type of sample like that, we come across that sample, then we're almost certainly going to sample it within the constraints of the engineering, of course. So we're going to we'll already have an idea of kind of a wish list, if you will, of samples before we get there.
Okay, great. It's always good to know what you're looking for. All right, we're going to go back to the phone lines with media questions. Irene Klotz of Aviation Week, go ahead.
Thanks. My question's for Dr. Parker. What is the ESA monetary contribution for the Mars sample return campaign?
Sure, happy to answer that. So the Mars sample return was one of the main elements that we put to ministers at the conference at the end of last year. And what we requested was the first roughly third of the funding for Mars sample return. And the overall budget over the whole decade is of the order of 1.5 billion euros. and we secured basically the first third of that at the ministerial last year in Seville in 2019, and the next part will be required at the ministerial at the end of 2022.
Thank you.
Thanks, Dave. Okay, next question comes from Mike Wall of Space.com.
Thank you all. Just a quick question about the sample receiving facility. What's the timeline, do you reckon, for the selection of that site, and sort of how will it be chosen? It seems like there will be a lot of sort of factors going into it. And what will it resemble? Will it resemble like a CDC facility that sort of works on Ebola? What are the sort of criteria that will go into the selection? What's the timeline for the selection of that site?
All right, I'm going to toss that to Lisa.
It's a very good question. It's a question on everybody's mind. Now that we've committed to the architecture and we have the funding from both the U.S. and European side, we need to start to make plans to get ready for that receiving facility. It's a long process because it will require the NEPA process in the United States, and that starts with an environmental impact statement, and it will involve many agencies. In fact, just in the last few weeks, an intergovernmental working group was established to start thinking about a national policy for planetary protection, and clearly the receiving facility is a big part of that. So I think you'll see over the next couple of years, we'll continue to study what the options are for essentially rehabbing an existing facility, building a new facility. I think that's unlikely, or using a more contemporary modular structure, which is used in many cases, particularly for particularly hazardous material. And yes, we sometimes refer to this as a BSL 4+. So something where we will certainly learn from how we handle the most dangerous contagious pathogens on Earth. Not that we really think there will be anything pathogenic or highly dangerous from Mars, but we're going to be extremely cautious. And as I said, that process is just getting started. It'll be several years while we work on the design, work on site selection, clear the NEPA hurdles, and then we'll be certainly ready to go a decade from now, which, as we've all been pointing out, 2031 is the soonest that these samples can be returned to Earth, and I think we'll be ready and waiting and so eager to get that canister back on the ground here so that the scientists can begin to address the exciting process of, for the first time ever, being able to examine materials that were scientifically selected on Mars and not just the random gift of meteorites.
Thanks, Lisa. Okay, we're going to go to Jeff Faust of Space News.
Hi, it's a question for Thomas or maybe for Jeff. Now that we've heard from ESA about their contracting plans and budget, can you give us at least a sort of a rough order of magnitude cost for the remainder of NASA's contributions to Mars sample return, and when will the contracting start to take place for the lander mission in 2026? Thanks.
Thanks, Jeff. Thomas here. The budget that we submitted to Congress and that is currently under consideration has, of course, an estimate. I just want to remind everybody that this is an estimate that is the first guess, and that first guess is kind of the order $3 billion, $2.5 to $3 billion, and that does not include yet all the kind of sophisticated equipment that will be part of that receiving facility, as well as the analysis methodologies that will be around that. And so I remind everybody, of course, that the way we're assessing the costs for these things is to actually go through a rigorous set of analysis and design cycles, and will culminate with what we call in the U.S. as confirmation or key decision point C, at which point the cost will be given. But where we are right now is $2.5 to $3 billion without these ground equipments. Needless to say, by the way, that facility that Lisa is talking about is very much a facility that we want the community internationally involved, and we welcome and we're really excited about really that facility to be a kind of a meeting point of the international science community of the United States, of Europe, and beyond. And I really believe that that will be one of those places that a lot of the innovation will come from, and a lot of the science will come from. So I hope that answered the question, Jeff.
Thanks.
Okay, we're going to go back to social media. So Shivam on Facebook asks, how did you propose the mission and who came up with the ideas? So I think maybe, Thomas, do you know the conception of this whole Mars sample return campaign?
It's really interesting to think about this. So first of all, the Mars sample return that we're doing is not the first one, the first singular mission that was designed to do that. This is perhaps the third or fourth iteration that good teams, really great teams over time, have tried to do that. This is the right time because we're ready and we have, in fact, perseverance there. What really mattered and what's just as important is two things. First of all, we got from the national academies in the United States, if you want a rating of this important mission that is actually was rated by them as the most important in that cost bracket. And so that basically means for us we need to invest our time and our efforts towards that. The second thing is the system engineering team at JPL, the team that I would argue has brought us actually curiosity, has brought us perseverance, is a team, and of course strengthened now with systems engineers from all over Europe as well, and other centers that are coming together and bringing everything to bear that we have. NASA centers and industrial partners are coming together, and really the first iteration that you see here as an end-to-end system is what we discussed, both Dave and I, and actually Jeff talked about it too. Make no mistake, this is, if history is a teacher, not the final kind of version of this. We're going to learn a lot as we go forward, which is precisely why I gave the answer to Jeff the way I did. So yes, it is the academies that prioritized it, and the system engineering teams at JPL that did all this. But make no mistake, that design keeps on going, and we're going to learn a lot in the next few months and years. I don't know, Jeff, is there anything you wanted to add to this important question?
Certainly, we're in the early design phases. We're approaching our first life cycle review in the NASA process, which is the mission concept review. That's going to happen this fall. So we're on our way. We're refining the design, and I think we're working closely with David and the European partners to refine it, and we're looking forward to hitting this and having a design that gets us to getting samples and as soon as 31. So I think we're on our path, and we have a great team, as Thomas described. We've got the right team.
All right. Himanshu on Facebook asks, are you sure you will be able to analyze a huge planet almost half the size of Earth with only 40 samples? So I'm going to toss that to Chris.
That's a great question. I think one of the key things about the landing site at Jezero Crater is that the rocks there, as far as we could tell from orbit, from the context that we know, are from a key time frame in Mars history, between about 3.5 to 4 billion years ago. And we know from other studies, other rovers and orbiters, that is a key time in Mars history when it transitioned from being a warmer, wetter environment at the surface with nice neutral water to being more acidic waters, and then eventually drying out and rusting and turning red like we see it today. So even though we're looking at a local area and a crater and associated sediments in the crater, we are also looking for other rocks that may be superimposed in the crater or just outside of the crater, other samples of opportunity that will also be able to fill in those those details, fill in those gaps for that key time frame in Mars history, and really understanding why Mars went from being probably habitable over most of its surface to being inhospitable as it is today.
All right, we're going to take one last question over the phone lines. Ken Kramer from Space Up Close.
Thank you very much for doing this. I think the question is for David Parker. The Fetch Rover, can you talk about what's its capabilities going to be? Is it going to be like Rosalind Franklin, or are you going to have a completely new design, and can you tell us what it will be able to do? Thanks.
Sure, thanks. The Fetch Rover, the key thing about it is not a science instrument itself. So compared to Rosalind Franklin, the big challenges on Rosalind Franklin are all about life search instrumentation, about cleanliness in a similar way that Lisa talked about the planetary protection issues. So we don't have the challenge of complex scientific instruments. On the other hand, we have a different set of challenges, which is it's a vehicle to go and collect those samples, find them, but to travel rapidly. And so conceptually, a lot of the technology is based on Rosalind Franklin, but it is smaller. It'll be about half the mass of the Franklin rover. But it has this ability to travel more rapidly. We've been doing a lot of work on autonomous navigation demonstrations on the Earth. And the Rosalind Franklin rover has in fact, two different versions of autonomous software that demonstrate on the surface of Mars. And so implementing that and relying on this rapid traverse across the surface is, if you like, the key challenge. And also the challenge that we're doing it without radioisotope devices. So it's another part of what Thomas called the kind of lean architecture for MSR, that we are trying to keep it as simple as possible in order to make this whole project deliverable. So it's a small, fast dune buggy. It's got 4 wheels instead of the usual 6, and they're of a novel design that NASA has been working on. It's going to use solar power, like Franklin, to do its job and get back. Basically, its mission on the surface is about 5 months, so it's really up against the clock. Hope that answers the question.
Okay, we're going to take actually one more question from the phone lines. We have Jake Robbins of the We Martians podcast.
Hey there, thanks for taking my question. I just wanted to know about the Mars Ascent vehicle. I know that the last decadal survey identified it as one of the trickiest pieces of hardware to develop, and there's been some studies on it. So can you give us an update on where we're at for developing that rocket?
I'm going to throw that to Jeff at NASA headquarters.
Sure, thank you. So yes, we're working the Mars Ascent vehicle design. We're actually in the middle of doing some trades to see what that's going to look like, but we're confident that we can get to a design that closes and does what we need to do to put the orbiting sample into orbit around Mars where it can be retrieved. So I'd say over the next few months we're going to converge on a final concept that we're going to look at going forward.
Right. Okay, so we're going to wrap up our show today, but there's so much more still to discuss and to watch. We have another news conference in about an hour at 4 p.m. Eastern Time. This is going to be about the technology that's flying with the Perseverance rover and also the future of human exploration. And then, of course, on July 30th, that's going to be the big day. We are going to have live launch coverage. That's going to start at 7 a.m. Eastern Time, and it's going to be a little bit painful at 4 a.m. Pacific Time, where my JPL colleagues are at. You can watch that on nasa.gov. If you want to learn more about the mission, we have the mission websites, nasa.gov/perseverance and mars.nasa.gov/perseverance. And please follow us on social media to get updates. You can find us on Facebook and Twitter at NASA Persevere. Thanks for joining us today.
Wherever, however,
whenever. We're here, there. We're everywhere.